All right, so good morning, everybody. It's my pleasure to introduce James Freitag from the University of Illinois at Chicago, and he will speak about not Pfaffian. Faffian, sorry.
Okay, thanks. So I'll try to explain exactly what Pfaffian means and what a Pfaffian function is. But I'll just mention, this is a somewhat unique experience in that I hadn't worked at all on Pfaffian functions up until this last spring, a year ago. And it's only because Gareth Jones gave a talk in this seminar where I learned about the problem that I'm going to talk about today. So so the seminar made a big impact on me. So I'll explain what a Pfaffian function is, not assuming that you have any background on it, not assuming that you followed Gareth's talk as closely as I did. So I'm going to give the definitions as well as some motivation about why this class of functions is studied. And then I'll mention an existing result, which is a little bit towards a result like mine, but in a very restrictive setting. And that's a result of Angus McIntyre's from about 15 years ago. And then I'll talk about the surprising connection between Pfaffian functions and one of the central topics in the model theoretic study of algebraic differential equations, which is called strong minimality. And I won't assume that you know what that means either. Okay, so let's get started. Why do people study Pfaffian functions? I'm going to give you a couple of different motivational points of view. The first comes from model theory, but not the model theory of differential equations. So this part, you don't need to fully internalize the definitions that I'm saying, but I think it's helpful to state them to give you a feel for why this notion is important. So there's a very important notion in model theory of a first order theory being called model complete. And a first order theory is model complete if any formula, any first order formula, so that's can involve quantifiers like for all and there exists, is actually equivalent to an existential formula. And so that's a formula which only involves the existential quantifier. So exists, x1, exists x2, etc. And then some quantifier-free formula involving those variables, and maybe some other free variables which don't get quantified over. So roughly speaking, this means that if you understand the quantifier-free sets in a model complete formula, every definable set, that is the set cut out by a first order formula, is equivalent to the projection of a quantifier-free set. Okay, so it's an important notion, although it's not so important that you internalize that now. But Pfaffian functions were studied because of model completeness properties by model theorists. And I'll say what those are in a moment. Okay, so I now want R star to be what I call an expansion of the reals with order. And so that just means that I take the normal ordering on the real numbers and I add to it some other primitive functions or relations. Like a popular thing to do would be to study the reals with addition and multiplication like normal and less than, so that the quantifier-free formulas exactly correspond to polynomial inequalities. Okay, so if you're in this setup, then if you know that any quantifier-free definable subset has only finitely many connected components in the normal Euclidean topology on the reals, and you know that the theory of R star is model complete, then there's this strong conclusion that the theory of R star is O minimal. And this, well, even if you don't know what an O minimal theory is, it's easy to say. This means that every definable subset of one variable, so of just the reals, is a finite union of points and intervals. And it turns out that being O minimal gives the theory of that O minimal theories have a tremendous structure theory, which has been exploited to solve numerous interesting mathematical problems. So, right. So verifying that a certain theory is model complete is a step towards showing O minimality. And well, what are some examples? So of course, it's a famous theorem of Tarski that any projection of a semi-algebraic set is semi-algebraic. So that means that, okay, semi-algebraic just means cut out by polynomial inequalities. So that means that the reals as an ordered field has the even stronger property that every formula is equivalent to a quantifier-free formula. Okay, well, there were results generalizing sort of Tarski's approach, classically studied in the 60s. So a semi-analytic subset of R to the n is one that's given by a Boolean combination of sets of the following form. Okay, so equalities of analytic functions in multiple variables and inequalities of analytic functions in multiple variables. Now, the projection of such a set turns out to not necessarily be semi-analytic. There are semi-analytic sets, so that when you take their projection, you don't get a semi-analytic set. But the projection of such a set is called sub-analytic. And Gabrielov showed that the complement of a sub-analytic set is sub-analytic, and from that it follows that this class of sets, if you have this as all of your definable sets, you're working in a model complete structure. So it follows that projections are sub-analytic sets are sub-analytic. And so the way in which this is all formalized from a model theoretic perspective is that one adds a big list of function symbols to the language of the real numbers with plus and times and order, which is symbols for every real analytic function, but just restricted to an n-dimensional box. And the function is defined to be 0 outside of that box. If you take that to be the collection of all of those, if you take f to be the collection of all such functions, then this language, which we call L-an, is an expansion of the language of ordered rings with a symbol for every such function. and we call the theory Tn. Okay, well, Gabrielov's theorem says that Tn is model complete. And model theorists wondered for a long time whether one could look at just certain subsets of the set of functions of f and still get a model completeness result. Eventually, that was proven by Alex Wilkie, and he showed that when you take the collection of functions, f1, which is a subset of these restricted analytic functions, if you take f1 to be the set of functions in what's called a Pfaffian chain, then you get a model completeness result. Okay, so that's really the motivation from the model theoretic perspective for why Pfaffian functions are so interesting to study. But we're going to have motivations from other perspectives next. Okay, first, I'm going to define Pfaffian functions carefully. Okay, so this won't assume that you know them, and I'll try to give some examples as well. So let f1 through fl be some real analytic functions on some domain. Okay, so it's just U is the common domain of all of these functions, and it's just some open connected subset of r to the n. Okay. I will call this list, and here the order matters. So I've written it, as an ordered tuple. I'll call this list of functions a Pfaffian chain if there are polynomials Pij, which depend on some variables x1 through xn. x1 through xn are just going to be the underlying coordinates of my domain here. My domain is in r to the n, and so these are just the coordinate functions on r to the n, okay? And v1 through vi, and I'll explain what the v1 through vi do in a moment. But this is just a polynomial, and the polynomial has coefficients in the real numbers, and it has the property that when you take the derivative of the ith function in your list with respect to the variable x sub j, it is a polynomial function of, well, the coordinate functions and all of the functions on the list which came earlier, including the function itself. Okay, so you can kind of think that the FIs satisfy a system of algebraic differential equations which has this triangular shape. I hope that this makes sense to everyone. This holds for all of the indices where this makes sense. So j ranges from 1 to n, and I ranges from 1 to L, the length of the chain. Okay, so from this, it's a little bit hard to understand exactly what kind of functions are Pfaffian, but I'll try to tell you that. Okay, so I'll call a function Pfaffian if it can be written as a polynomial of functions in a Pfaffian chain. Okay, all right, so let's see some examples of this. The first example I want to give is where f is a rational function, p over q, where p and q are polynomials with real coefficients. Here, if I take f1 to be 1 over q and f2 to be f, then f1 comma f2 is a Pfaffian chain. To see that, you have to take the derivatives of those elements. Well, that's not hard. The derivative of f1 is q prime times f1 squared. So that's fine. That's a polynomial times the function itself. Okay, so it satisfies this triangular form. f2 prime can be written in this way, this polynomial times f1 squared. And f1 came earlier on the list for a reason. So again, this satisfies this sort of triangular form of differential equation. So f1, f2 is a Pfaffian chain. Any rational function is Pfaffian.
So James, in this case, this is a one variable rational function.
Oh, yeah. Sorry, I'm just giving the examples for one variable functions because I think for multiple variables, it's also true. But I think, for purposes of an example, it's easier to just internalize the one variable case.
Thank you.
Okay, but many other functions are Pfaffian, not just rational. So you can see that if you take f1 of x to be 1 over 1 plus x squared, okay, of course, that can be the first element in a Pfaffian chain by essentially the previous example. And you take f2 to be the inverse tangent function. Well, if you've taught calculus recently, then you know that f2 prime is f1. Okay, and we just saw what f1 prime is. That's a special case of the above example. And so again, here, f1 comma f2 is a Pfaffian chain. Okay. If you want to think about trig functions rather than inverse trig functions, the derivative of the tangent function is tangent squared plus 1. So that can be the first element of a Pfaffian chain. That can be f1. Okay, so I can take, let me sort of write this in another color. I can take f1 to be tangent of x. And I can take f2 to be the sine of 2x because that has derivative 2 tangent x over 1 plus tangent squared x. Okay, so right. So again, this has the necessary triangular form, and you can use this sort of technique here that I think you can see how it generalizes to see that well, bounded trigonometric functions are Pfaffian. Now, so since I had the domain of my functions in my chain all have a common domain U, I'm restricted here to, at least by this technique, to the domain being a place where the tangent function is defined. And so that's going to have to be a bounded domain. I need to avoid the places where cosine is 0. Okay, so bounded trigonometric functions are Pfaffian by this argument. Okay, but plenty of other functions are Pfaffian too, and I'm not going to give an exhaustive list. In fact, we don't know how to give an exhaustive list. That's part of what this talk is about. But here are some other functions that are Pfaffian. Any algebraic function like square root on a suitable domain, or just roots of arbitrary polynomials are Pfaffian, and compositions of Pfaffian functions are Pfaffian. There, you have to be careful about the domain, but so compositions where the composition makes sense. Okay, all right. So another big motivation for studying Pfaffian functions, and the reason that they were actually introduced in the first place, comes from work of Handson. And I think that Handson named this class of functions, and I'm not sure exactly why he named them this. Probably it has something to do with the form of the differential equations they satisfy. Okay, so if you take a collection of Pfaffian functions and you have them come from some Pfaffian chain with some and you let them come from a Pfaffian chain in the sense that each of them is a polynomial function of the Pfaffian chain, and you know the degrees of the QIs that appear, and you know the degrees of the polynomials that appear in the definition of the Pfaffian chain, the degree of the differential equations that's appearing there. then it turns out that the number of components in the set cut out by, so you can look at the set of x bar, sorry, I didn't write this, in r to the n, such that f1 of x bar equals fm of x bar, the zero set of all of these functions. This is the set that I'm talking about here. For some reason, I didn't write it down, but the sum of the Betty numbers of this set, and it's not important what that is. You can just read this as, this is a generalization of what I'm going to say. Instead, the number of components of this set here, this zero set, is bounded by a completely explicit function of the degrees of the QIs and the degrees of the polynomials that appear in the chain. So you have an estimate, a completely explicit estimate from the differential equations for, say, the number of zeros of such a set when this set is discrete, when it's zero dimensional. Okay, which of course is not something that you have in general for analytic functions, because in general, the number of zeros of a zero set of some analytic functions could be an infinite discrete subset of r to the m, like the sine function, vanishes at the integers times pi. Okay, so so this theorem of Khovansky is really strong motivation to study this class, and we'll have even more motivation in a few moments. But let me also mention that I'm interested in the notion, a similar notion, but for analytic functions of a complex variable. Okay. And the definition is exactly the same, except that you replace real analytic with complex analytic, although the class of functions is much different. Okay, and well, it shares some characteristics, but I'll tell you an important difference. Okay, so if you take some complex analytic functions on some domain, they form a Pfaffian chain if they satisfy this, again, sort of triangular system of differential equations. And a C-Pfaffian function is one that's a C polynomial of functions of a C-Pfaffian chain. And so you can easily see that the complex exponential function is C-Pfaffian, right? Because its derivative is just itself. That satisfies my triangular form with just the polynomial being the identity function on f1 and the exponential function being f1. But of course, the zero set of this function doesn't satisfy anything like Khovansky's theorem. Okay, so you don't have those kinds of estimates unless you're very careful about the domain in the C analytic world. Okay, so why are we interested in Pfaffian functions, or at least why was Gareth so interested in Pfaffian functions when he talked in this seminar? I'll tell you, it has to do with O minimality again. So there's a theorem in O minimality which has been tremendously influential in the last 15 years, called the Pila-Wilke counting theorem. And what it says is that if you have a subset of r to the n, which is definable in an O minimal expansion, and well, by Wilke's theorem and Gabrielov's theorem, the elements from a Pfaffian chain form an O minimal expansion. Okay, but we don't need to know that so much. Well, if that's true, then for all epsilon greater than 0, there is a constant such that this set, I'll tell you what it is in a moment. This is the number of points in what's called the transcendental part of the set X of height at most t. So it's the number of rational points in that set. Okay, so this is the number of rational points of height at most t. And the height of a rational number is just the max of the numerator and the denominator in absolute value. And the height of a tuple of rational numbers is just the max of the heights of the rational numbers in the list. Okay, so the number of rational points of this height is bounded by this sort of function. It's not so important to understand this theorem completely, but I will say what the transcendental part is. The transcendental part is, well, you have to remove all of the algebraic curves that go through your set. And that collection of algebraic curves is called X-alg. Once you remove that set, you get the transcendental part of X. I think I'm going to skip giving any example in the interest of time. But there's some questions that you can ask about the Pila-Wilke theorem. And I think the main questions are, how can one improve the theorem? And in general, you can't. But you might ask for a better asymptotic, or you might ask for an effective constant. And of course, you can't do either in general. But work of Gal Bignamini and Dmitry Novikov, Gareth Jones and Margaret Thomas, and really recent work of Bignamini and Novikov, also with the student Zach, do this. They accomplish better asymptotics and effective constants in the Pila-Wilke theorem. And they do this for certain sets defined by Pfaffian functions. But it's impossible to tell for which analytic functions those apply, because we don't know which analytic functions are Pfaffian. Here's an example. So Bignamini and Novikov say, well, the modular category currently appears to be more challenging. We have no reason to believe that J function is Pfaffian. So they didn't know whether the J function was Pfaffian. Because of that, a student of Pila, John Armitage, went to a lot of trouble to develop alternate methods for bounding the zeros of polynomial functions of the J function. Well, the problem is that basically, before I started working on this, I tried to look and see what are the ways in which one can show a transcendental function is not Pfaffian. The ways I discovered were, you show that it's a differential transcendental function, like the gamma function. That can't be Pfaffian, right? I mean, it can't satisfy any differential equation. So you're not going to make it satisfy one with a triangular form of its system. And the second one is to know some very particular analytic properties of the function, like its oscillation, and use that to violate Hovanski's theorem on the number of zeros. Or most likely, if you, in all the examples I know, you not only get a violation of Hovanski's theorem, but the violation is strong enough to violate O minimality. Well, the problem with approach number 2 with regard to the J function is that if you restrict to the fundamental domain, and here's these 2 reasons again, so the J function is not differentially transcendental, and if you restrict to the fundamental domain, it turns out that it is interpretable in an O-minimal structure, R and X. Okay, well, so to sum it up, many or most interesting functions are not in class 1. Many analytic functions we study because of their differential equation. So some not, right? So, some like the gamma function are differentially transcendental, and most likely then we study them because of a difference equation. But many times you can restrict the domain of a function to prevent 2. And that's the case with the J function. So if you include the J function on all of the upper half plane, of course, it's not O-minimal, it's doubly periodic by SL2Z. So can't be O-minimal. But I mean, if you restrict the domain, you may still want to know whether the J function restricted to its fundamental domain is O-minimal, as Binyamini and Novikov wanted to know. Okay, so let me quickly just give you a hands-on proof of why the J function can't satisfy a really, really simple differential equation. And then I'll explain how the main theorem that I proved generalizes this. So why can't the J function satisfy a Pfaffian type equation and be in a chain of length 1, just itself, okay? If that was going to happen, you'd have to have the J function satisfying a differential equation like this. And okay, I mean, and the F would even have to be polynomial, but let's just let the F be rational and prove that that can't even happen, okay? So, well, you know that the J function is SL2 invariant, so you can act on the variable by the action of SL2 acting by linear fractional transformation. And, you know, a consequence of that is that J of Z plus 1 is J of Z. So that means that J prime of Z plus 1 is J prime of Z. I mean, just if the functions are the same, their derivatives are the same. So J prime of Z is, let's say, this function here. But then this is a rational function. And so, I mean, we know that because J prime is equal, I can put Z plus 1 everywhere I see Z, because F of Z plus 1, J of Z plus 1 is J prime, and J prime of Z is J prime of Z plus 1. So we have this equals this. But now J is itself SL2 invariant. So I can do that. I can change J of Z plus 1 to J of Z. And this holds for any X, well, it holds for generic X, Y, and C2 for various reasons, which I won't say. But then it has to hold everywhere. And so F of X, Y equals F of X plus 1 comma Y. But, well, that just means that F is only a function of Y, right? You can't have that kind of equality for a rational function. So that's a problem, because now we have J prime of Z equals F of J of Z. And this function here is SL2 invariant. And this function here is what we call a quasi-modular form of weight 2. And that just means that when you act by linear fractional transformation on the variable Z on the inside, it transforms in this way here, where this exponent is a 2, not a 0, as it would be for this function here. Okay, so it can't satisfy that differential equation. I think it would be interesting to see if someone could, you know, generalize this argument here, just give a completely hands-on argument that the J function is not Pfaffian. I wasn't able to see how to do it personally. I mean, I tried it only for the simplest kind of equation and succeeded, tried it for other equations and found that I couldn't. Okay, so, and I'll just mention theorem of McIntyre real quick. Actually, you know, I think I'll skip this theorem of McIntyre because I want to state my theorem before I run out of time. Okay, so so I'm working now with differential equations, and sorry, I need to skip some of what I was going to say. But here's a theorem due to Scanlon, well, myself and Tom Scanlon, and it turns out that the J function satisfies this differential equation. And it turns out that differential equation is strongly minimal. Now, let me just explain to you what, in down-to-earth terms, strong minimality of that equation means. Okay, because I don't I don't have time to define it. So strong minimality of that equation means that if you take any solution to that equation, so okay, so let's say that the equation you're talking about is defined with coefficients from a differential field K. And we take any differential field extension of K and any solution to the equation X. Then the transcendence degree of the differential field extension generated by the solution over F is either the transcendence degree of the differential field extension generated by the solution over K, that is the order of the original equation, or 0, because F is algebraic. Okay, so I don't have time to explain why this is such a central topic in modern study of differential algebra by model theorists, but you can use this to prove that the J function can't be C-Pfaffian. In fact, you can use it to prove that it can't even be algebraic over any C-Pfaffian chain. Okay, so in the case of the J function, what does strong minimality mean? It means that the transcendence degree of a solution of the equation satisfied by the J function is either 0 or 3 when you take its derivatives. Well, so how can you see that this precludes being in a Pfaffian chain? Well, take L to be the minimal length chain such that the J function is algebraic over F1 through FL. Okay, so this is like for a contradiction. So J of Z algebraic over F1 through FL. Well, then the J function is transcendental over the chain F1 through FL minus 1. Okay, but I mean, if you think about this Pfaffian condition, the field, just the field generated by Z and F1 through FL minus 1 is actually a differential field, because the derivatives of the generators of that field are written as a polynomial combination of the earlier things that appear. Okay, so this is actually a differential field. And so this condition here applies. And so that means that the J function and its first and second derivatives have to be transcendence degree 3 over this field here. But over that field, the field F of FL, that has transcendence degree 1. And so it can't be that J prime and J double prime are contained in F of FL. But F of FL is a differential field. So if it were to contain J of Z, or even if J of Z were algebraic over it, then J prime of Z and J double prime of Z would be algebraic over the field as well. And so we've seen that's impossible. And so the conclusion is that the J function is not algebraic over any C-Pfaffian chain. Okay, let me just make a couple of quick remarks on this, and then I know it's time to move to the next segment. The first remark is that nothing about this depended at all on the J function itself. This would work anytime the analytic function that you pick satisfies a strongly minimal differential equation of order larger than 1. Okay, so it's a pretty general theorem. It's very easy to prove. Slightly harder to prove is the real analytic version of this. And you can prove that the real and imaginary parts of the J function can't be algebraic over any real Pfaffian chain. And the technique of the argument is really similar, but you just have to be much more careful. And you do have to use carefully the fact that the function whose real and imaginary parts you're taking is C analytic. Okay, so I think I'll end there, and I'll just say, I learned about this problem. Gareth asked the question whether the J function was Pfaffian in the spring Colchin seminar like a year ago, and then after that I decided maybe I should try to work on this since I'd worked on the J function a lot. This answers a question of Bignamini and Novikov, but it also answers some other questions around minimality and algebraic differential equations, which I think I didn't have time to mention. That was in the middle part of the talk. Some questions of Bianconi and some others. So thanks very much.
Thank you. So let's thanks James for his talk. So do we have any questions for James?
Can I have a silly question?
Mm-hmm.
Is the empty chain considered Pfaffian?
The empty chain?
Yeah.
Oh, I don't know, but why would it matter?
Well, because you sometimes say the F1 up to F sub L minus 1.
Oh, I see. Yeah, I think, well, I guess in that, yeah, I would consider it Pfaffian because in that case, the field that in that case of, say, the proof, the field that you're talking about would just be the field C of Z, the field of rational functions. Yeah.
Right. Yeah. So any function would be, right?
Well, any rational function,
right,
would be in that field, but
right. Okay.
But yeah, but certainly, I mean, no, to be a Pfaffian function, you have to satisfy this very particular, triangular sort of differential system of, order 1 differential equations. And the truth is, as you might get some indication from my talk, it's really not known what the class of Pfaffian functions includes. With respect to many classically defined analytic functions, we really don't know. So for instance, it wasn't known whether the J function was Pfaffian.
Hi, I have a question.
Yeah.
It's naive. So the definition of Faffian is that the derivative of the function is, let's say, is polynomial in the function previous.
Yes.
If you're weakening that definition to it being algebraic, first of all, is that really a weakening? No,
it's not. That's a good question. So the reason that Hovanski's definition is the way it is that he was really interested. So yeah, you can show that algebraic functions of Pfaffian functions are Pfaffian. And from that, that can be used to answer your question. The reason that Hovanski's definition is the way it is that he was interested in getting these very specific, like completely explicit bounds on the number of zeros, or more generally the Betti numbers of these sets defined as zero sets of Pfaffian functions, in terms of what he calls the complexity of the chain, which is basically the tuple of degrees of the polynomials that appear in the defining equations. And so if you would set it up in the way you suggest with algebraic functions, you would have to like track this other data. You could do it that way, I think. But somehow, somehow it's simpler to do it just with degrees of polynomials.
Okay, thanks.
Are there any other quick question? I have one, but I'll keep it for after.
Okay, yeah, sure.
All right. So let us thank James again. I will go out
Okay.
to breakout rooms. Thank you, James.
Thanks.